Now let's see if we can interpret that demonstration with a little bit of math. The first thing to note is that in helium, the speed of sound is faster than it is in air, as we'll just show in just a moment. But if we look at the master equation, if you increase the speed and keep the wavelength the same, then the frequency will increase. So what does the wavelength depend on? That depends on the resonation chamber, which is just his lungs, a single open-ended tube, closed on the bottom, open on the top. So if you keep the wavelength the same, but increase the speed, the frequency will increase, which is why his voice sounded so high when he breathed in the helium. Frequency went up. And the converse, of course, is true with the sodium hexafluoride. Sound has a speed that is lower in that substance than it is in air, so the frequency went down. Let's do a few checks for understanding. Which is harder to compress, hot air or cold air? And keep in mind, hot air, the molecules are moving around very, very fast, slamming into the walls of the balloon or whatever they're in, or cold air, where they are moving very slowly. Well, it is in fact true that hot air is harder to compress, assuming the same density. Now, which has higher bulk modulus? Well, that's really asking the same question. Hot air has a greater bulk modulus. It's harder to compress. Hot air is more like this, hard to compress, than this sponge, which is easy to compress. Now, again, if we keep constant density here, so we're not changing the density, which would sound travel faster through, hot air or cold air? Well, if you just look at the equation for the speed of sound, it's the square root of the bulk modulus over the density. So if the bulk modulus is greater, sound would travel through hot air faster. In fact, V is about, speed of sound is about 331 meters per second at 0 degrees Celsius, and it's closer to 343 meters per second at 20 degrees Celsius. You can see that it does travel faster at higher temperature. Now, how about this? A water molecule has mass 18 atomic mass units. Nitrogen at 28 atomic mass units. Nitrogen has actually a higher mass per molecule than water molecules do. And oxygen has an even higher mass per molecule of 32 atomic mass units. But compare nitrogen and oxygen, which air is mainly made out of, to water, which has 18 atomic mass units. It's less heavy per molecule. In humid air, the lighter H2O molecules, they displace the nitrogen and oxygen molecules, the N2 and O2. In other words, everywhere that there's a water molecule, that's one place that nitrogen or oxygen can't be. So humid air has actually lower density. Humid air has lower density. That is a non-intuitive fact, but it's true. Humid air is less dense than dry air. Which one will sound travel faster through? Well, if you assume that they're the same squishability, which they pretty much are, turns out sound travels faster through humid air. It's less dense. Look right up here. If the lower the density, the higher the speed of sound. Next, let's use this table of some bulk moduli and densities for several different substances and try to figure out the speed of sound in those substances. And the ones we're going to analyze right now are some common substances such as helium, air, water, and steel. And you might try to predict which one you think will have the fastest speed of sound. Let's start with helium. Helium of these substances has a relatively medium to low bulk modulus. Its bulk modulus is 1.69 times 10 to the fifth newtons per meter squared. So 1.69 times 10 to the fifth newtons per meter squared. To find out the speed of sound, we divide that by the density, which is also pretty low here, divided by 0.1663. And then we got to take the square root of that. So we're getting, for the speed of sound, about 1,000, I'm going to stick to 3 sig figs. So that's about 1,010 meters per second. 1,010 meters per second for helium at standard temperature and pressure. Let's try it for air. You might already guess, having seen that demo, how the speed in air differs, but let's go ahead and try it. Now, it's got a slightly higher bulk modulus, slightly lower. It's a little bit easier to squeeze air down, 1.42 times 10 to the fifth newtons per meter squared, but it also has a higher density. So that, of course, is going to, divided by 1.204, and then we have to take the square root of that, and then we get 343 meters per second. So that's kind of what we expected before, 343 meters per second. Now, how about water? If we look at water, it's got a much higher bulk modulus. Water is really difficult to squeeze, and it's often considered incompressible. So with a much higher bulk modulus, you might expect it to have higher speed, but it also has higher density as well. So let's see what happens for water. Let's go ahead and do the calculation. Complete the calculations for the speed of sound in water and steel, and include them in your notes for this section. You might try to predict beforehand which one you think has a greater speed of sound, water or steel.